Practically, if we design the power converters, we'll see that the equivalent series resistance of the capacitor plays a very important role in the converter dynamics. So it is very important to include the capacitor ESR to model the AC system for the power processor. So now let's utilize the boost example to show how can we use state space averaging method to derive its equivalent AC model considering the capacitor ESR. So first, let me plot the boost circuit schematic with the capacitor ESR. So for boost topologies, we have the input port here, and the inductor is connected directly to the input source. And here is the MOSFET. So here is the inductance, here's Q. And here's the diode. So for the capacitor, it usually comes with a equivalent series resistance. We use a resistance here to denote its ESR. So here we use RC to denote. And this is capacitance C. And load resistance R. Here's the output voltage. Based on the boost circuit with ESR, we also need to define the quantities, polarities, and directions. For example, here's the inductor voltage, and here's the inductor current. And here is the capacitor current. And here is the capacitor voltage as VCT. So we care about those parameters very much because they are closely associated with the energy storage units. Right? For such a non-ideal system, we should pay special attention to the capacitor voltage because previously we have the principle of, we call it small ripple approximation. Remember, this principle is mainly for capacitor voltage, especially for the filtering capacitor voltage. For here, it is still valid for capacitor voltage, which is VC. We mark it, means that it is still applicable. However, for the output voltage, VT, which is equals to the capacitor voltage plus the resistor voltage drop. For this VT, we cross it because we can no longer apply the small ripple approximation to the VT analysis. Indeed, we can try to quantitatively analyze it. So we can plot the time domain profile for the output voltage. At a steady state in time domain. So here is the output voltage. So we'll see a two-step waveform. So in model 1, from 0 to DTS, the value for the output voltage will be equal to this quantity. So we consider in model 1, diode is off, right? So capacitor provides current to RC in series with R. So the output voltage will be equal to capacitor voltage divided by this voltage divider network. So actually, the level here will be equals to VC times voltage division ratio, R plus RC. And for the operation mode 2 from DTS to TS, so you will see that the delta is conducting, right? Delta is conducting, it's like Q is off. So the IL will charge capacitor and provide current to R. So this value will be contributed by two parts. The first part is we consider IL independently. This will contribute to a V. And the second part is we consider VC independently. This will also contribute to a output voltage. So by the principle of superposition, we can find out the value for V in mode 2 will be equals to the sum of those two parts. So the first part is identical to the stage 1. And this gap, the difference, is contributed by the inductor current part. So this delta equals to inductor current. So we only consider I, meaning that we ignore this voltage source, so that RC is in parallel with R. So the contribution of this current to this parallel will be equals to the current times the equivalent resistance, which is the parallel of RC and R. So you will see that the output voltage will have a two-step profile. Step 1 is voltage division profile. Step 2, we plot the contribution of the inductor current. So this is basically the delta V. Okay. So now let's try to use the state space method, right? So we first need to define the state vector. So we have two energy storage units, right? So basically X is the state vector will be equals to inductor current, capacitor voltage. And next is the input vector. Input vector, we only have one external independent voltage source. So the U equals to the voltage, input voltage source, which is also time varying, right? And the output vector we have the Y equals to, so we define the output voltage as the desired output signal. So this will equals to output voltage. Then we analyze the two operation modes for boost converter. First, we consider mode 1. So first, let's consider mode 1. We can plot its equivalent circuit. In mode 1, the Q is on. We consider it's a short circuit. So we will have the resulting equivalent circuit. Here is input source. Here is the inductor Q is on. And for the output port, diode is off. RC. R. So that is the equivalent circuit. To save time, I no longer mark the polarities and directions. You can refer to here, okay? Then we can write those three critical equations. First one is the inductor of current, L di L over dt. So this equals to the input voltage, right? Input voltage. Second is the capacitor voltage derivative. So C dVc over dt. So this equals to the capacitor current based on the KCL in this node. We can see that this equals to the minus voltage divided by the series of RC and R. And last one is the output equation. So the output voltage, right? Output voltage Vt. So as we mentioned that this is like a voltage divider behavior, which divides the capacitor voltage by the division ratio, right? So this equals to capacitor voltage times R over R plus RC, as what we already wrote here, right? Then we can use matrix to denote these three equations. First is the state equation. So derivative over dt for the state vector IL Vc. And we put the coefficient matrix K as L0, 0, C. And two parts on the right-hand side, right? One part is state vector plus the input vector by comparing those two equations, we can fill the blanks. So this equation corresponds to the first line, right? So we'll see that 0, 0, because we only have a VG term, right? So it's like 1, 0, 1. And the second line corresponds to the second equation. So it's 0 minus 1 over R plus RC, and here 0. So this is the matrix format. We can also use the symbols to denote, right? So here is like K derivative X over dt. And this one is A1 state vector plus this one is B1. Input vector. And next, for this one, right, for this output equation, we can also use the matrix format. So the output voltage equals to state vector IL Vc plus input vector Vg. Then fill the blanks, right? So here is like 0, and this one, right? 0. R over R plus Rc, 0. So similarly, we can write the standard equation. This one is y t equals to C1 x plus E1 U. So next, let's process what happens in operation mode 2. We can also plot the equivalent circuit correspondingly. The switch is off, diode is on, right? So here is the voltage source. Inductor is connected to the low side. Here is the RC, C. R. Here's output voltage, V. So similarly, we can write the state equations and output equations based on KVL and KCL. So first is the inductor current, right? L DIL over dt. This equals to the inductor voltage. By KVL, we can see that this is equals to Vg minus with output voltage. And for capacitor, the C dVc over dt, which is the capacitor current. By KCL in this node, we can see that this will be equals to this voltage minus the voltage, right? Because we didn't define this is the positive current. So this current equals to the current flowing through RC, which is the voltage drop across RC divided by the resistance. So Vt minus Vct over Rc. And the third one is the output equation, Vt. Vt, right? Vt, we have learned that actually here, by superposition principle, it includes two parts. This part plus delta. We can write the expression for mode 2 Vt. So contribution of the capacitor voltage plus contribution of the inductor current to the low side, which is delta V, which is IL. The parallel of R and RC. So next, we can insert this Vt to here and here to get the complete expression for inductor voltage and capacitor current. So you will, after you insert Vt to here, you will obtain Vgt minus Vct times voltage division ratio minus this quantity, IL, parallel of R and RC. And for this one, insert Vt to here, right? So this is minus Vct T over R plus RC. R over R plus RC. You will see that by doing this, we have fully eliminated VT terms in the inductor and the capacitor equations, right? So we can have the state vectors VC, right? State vector VC and IL to denote inductor voltage and capacitor current. Then we convert it into matrix format. So combining the top two, we have derivative over time, state vector fill the blanks. This is a K, right? L0, 0C equals to separate, I use equals to state vector parts plus the input vector part. Then fill the blanks for the 2, 2, 2 matrix and 2, 2, 1 matrix. So this is the first line corresponds to the first equation. So here is the minus R parallel with R C, right? This one. This one will correspond to this one, which is minus R over R plus RC. And this blank corresponds to this term, which is 1. For the second line, we read from the second equation, right? See, IL term is R over R plus RC. VC term here, minus 1 over R plus RC. And the VG term, there's no VG term, right? So here we fill 0. Then we use the symbols to denote, right? Here is K derivative X over dt equals to, this one is for mode 2, so A2 X plus, this one is for mode 2, right? B2 U. And then we process this one, right? We convert this one to matrix format, so which will have output vector equals to the contribution of the input vector plus the contribution of the state vector and the input vector. Then fill the blanks. We read directly here, right? So IL terms are parallel with RC. And the VC term is the voltage division ratio, right? So R divided by R plus RC. And the VG term, there's no VG term here, so this is 1. Then we can convert it into standard format. So we'll have Y T equals to, this one is C2 X plus E2 U. Okay, till now we have fully obtained the SSA, the matrix equation for mode 1 and mode 2 separately. And this model is based on we considering the equivalent series resistance of the capacitor. And the following step will be similar as what we did for buck boost converter. So we can do the state space averaging to calculate the average A, average B, average C, and average E. And also we can introduce the small signal perturbation and do the linearization. So by keeping only the small signal AC term, the first order small signal AC terms, we can obtain the small signal model for the boost converter with ESR. Then we can also get the equivalent circuit model for the non-ideal boost converter. So if you are interested, you can do yourself after my lecture.